When dealing with a new 200 amps single-phase 120/240 volt service, proper grounding is crucial for safety and code compliance. Considering the scenario where the service passes through a meter base, then to a 200 amp single-phase 120/240 volts fuse disconnect, where the neutral is bonded to earth ground, and a conduit connects the disconnect to a 42-space electrical panel elsewhere in the building, the question arises what size ground wire should be carried from the disconnect to the panel. Assuming the feeds are 4/0 for the hots, are 4/0 for the neutral, and a number 2 on the ground to the disconnect, determining the correct ground wire size is essential. According to the National Electrical Code, specifically section 250.30. A2, the grounding electrode conductor, often referred to as the GEC, for a service of 1000 amps or less, must not be smaller than the largest ungrounded conductor. In the described scenario, the largest ungrounded conductor is the 4/0 service conductors. Therefore, the grounding electrode conductor must be a 4/0 conductor. Further, National Electrical Code section 250.24. C3 addresses the equipment grounding conductor, also known as the EGC, for service of 1000 amps or less. It states that the equipment grounding conductor shall not be smaller than the grounding electrode conductor. As the grounding electrode conductor is determined to be a 4/0 conductor, the equipment grounding conductor must also be a 4/0 conductor. In summary, for this specific 200 amp single-phase service configuration, both the grounding electrode conductor and the equipment grounding conductor must be a 4/0 conductor to meet the requirements outlined in National Electrical Code sections 250.30, A2 and 250.24. C3. This ensures proper grounding and electrical safety for the system. To elaborate further, let's delve into the functions and importance of grounding conductors. Firstly, the grounding electrode conductor, also known as the GEC, connects the service equipment, typically the neutral bus within the service disconnect, to a grounding electrode system. This grounding electrode system usually comprises items like ground rods, metallic water pipes, or concrete encased electrodes, also known as UFERs. Its primary function is to provide a low impedance path for fault current to return to the source, which in turn facilitates the operation of overcurrent protective devices such as circuit breakers or fuses. Secondly, the equipment grounding conductor, also known as the EGC, on the other hand, is responsible for connecting the non-current carrying metallic parts of electrical equipment, such as the metal enclosures of panels, disconnects, and conduit systems, back to the service equipment. This ensures that in the event of a fault where a live conductor comes into contact with the metal enclosure, a low impedance path is available for fault current to flow, again triggering the overcurrent protective devices. Sizing these conductors correctly is not just about meeting code requirements, it's about ensuring the safety of people and property. Undersized grounding conductors can lead to elevated touch potentials on metallic equipment during fault conditions, posing a shock hazard. They can also impede the rapid clearing of faults, potentially leading to equipment damage or even fire. When selecting and installing grounding conductors, it's important to consider the material. Copper is the most commonly used material due to its excellent conductivity and corrosion resistance. Aluminum conductors are also permitted, but they must be sized larger than copper conductors to achieve equivalent ampacity. The installation method is also critical. Grounding conductors must be securely connected to the grounding electrode system and to the equipment they serve. Proper bonding techniques, using listed connectors and hardware, are essential to ensure low impedance connections. Furthermore, it's crucial to avoid practices that can compromise the integrity of the grounding system. For instance, daisy chaining grounding conductors from one piece of equipment to another can create high impedance paths and reduce the effectiveness of the grounding system. Each piece of equipment should have its own dedicated grounding conductor that runs back to the service equipment. In this specific scenario described, where a conduit connects the disconnect to a remote electrical panel, the conduit itself can serve as the equipment grounding conductor, provided it's properly installed and meets the requirements of the National Electrical Code. However, It's generally recommended to install a separate equipment grounding conductor within the conduit to provide a redundant grounding path and ensure optimal performance. In addition to sizing and installation considerations, regular inspection and maintenance of the grounding system are also important. Grounding connections can corrode over time, especially in damp or corrosive environments. Periodic inspections should include visual checks of grounding connections, as well as testing to verify the continuity and impedance of the grounding system. Any damaged or corroded components should be replaced promptly to maintain the integrity of the grounding system. It's also worth noting that the National Electrical Code undergoes revisions every 3 years, so it's essential to stay up to date with the latest requirements. Changes to the code can impact grounding requirements, so it's important to consult the most recent edition of the National Electrical Code and any applicable local amendments. Now, let's address some potential scenarios and common misconceptions related to grounding. One common misconception is that the grounding conductor only carries current during fault conditions. While it's true that the grounding conductor primarily serves as a fault current path, it can also carry small amounts of current under normal operating conditions due to imbalances in the electrical system. These currents are typically very small and don't pose a safety hazard, but it's important to be aware of their presence. Another potential scenario is when dealing with existing electrical systems that may not meet current code requirements. In these cases, it's important to assess the existing grounding system and make any necessary upgrades to bring it into compliance with the current code. This may involve replacing undersized grounding conductors, adding supplemental grounding electrodes, or improving bonding connections. It's also important to consider the impact of any modifications or additions to the electrical system on the grounding system. Any new equipment or circuits must be properly grounded to ensure that the overall grounding system remains effective. When working with electrical systems, it's always best to err on the side of caution and consult with a qualified electrician or electrical engineer if you have any questions or concerns about grounding. They can provide expert guidance and ensure that the grounding system meets all applicable code requirements and safety standards. In conclusion, proper grounding is a critical aspect of electrical safety. By understanding the requirements of the National Electrical Code and following best practices for installation and maintenance, you can help ensure that electrical systems are safe and reliable. Remember to always consult with a qualified professional when working with electrical systems, and never take shortcuts when it comes to safety. Now let's think of some common mistakes that people could run into while working on grounding. One of the most common mistakes is using the wrong size grounding conductor. This can happen due to a misunderstanding of the National Electrical Code requirements or simply due to carelessness. It's essential to carefully calculate the required size of the grounding conductor based on the size of the ungrounded conductors and the applicable code tables. Another common mistake is improper bonding of metallic enclosures and equipment. This can occur when using the wrong type of connectors, failing to clean surfaces before making connections, or neglecting to tighten connections properly. Poor bonding can create high impedance paths for fault current, reducing the effectiveness of the grounding system. Another issue is neglecting to protect grounding conductors from physical damage. Grounding conductors should be installed in a manner that protects them from abrasion, corrosion, and other forms of damage. This may involve using conduit sleeves or other protective measures. Sometimes people will forget to connect the grounding electrode conductor to the grounding electrode system. This can happen when installing new electrical services or when making modifications to existing services. Without the proper connection to the grounding electrode system, the grounding system will not be effective in providing a lower impedance path for fault current. Another potential issue is using the metallic water pipe as the sole grounding electrode. While metallic water pipes can be used as part of the grounding electrode system, they should not be the only grounding electrode. The National Electrical Code requires that other grounding electrodes, such as ground rods or concrete-encased electrodes, be used in addition to the metallic water pipe. Another mistake is that installers might not be aware of local amendments to the National Electrical Code. Local jurisdictions may have their own specific requirements for grounding, which may differ from the National Electrical Code. It's important to check with the local electrical inspector to ensure that the grounding system meets all applicable requirements. People might not be aware of the importance of regular inspection and maintenance of the grounding system. Grounding connections can corrode over time, especially in damp or corrosive environments. Regular inspection should include visual checks of grounding connections, as well as testing to verify the continuity and impedance of the grounding system. One mistake is ignoring the manufacturer's instructions for grounding equipment. Electrical equipment is often designed with specific grounding requirements which are outlined in the manufacturer's instructions. It's important to follow these instructions carefully to ensure that the equipment is properly grounded. One common mistake is assuming that the neutral conductor is always an adequate grounding path. While the neutral conductor is grounded at the service equipment, it is not intended to serve as the primary grounding path for fault current. Equipment grounding conductors should always be installed to provide a dedicated low impedance path for fault current. Grounding to gas pipes is also something that happens. Gas pipes should never be used as grounding electrodes. Gas pipes are not designed to carry electrical current and can pose a significant safety hazard if used for grounding purposes. When dealing with sensitive electronic equipment, such as computers or medical equipment, it's important to use proper grounding techniques to minimize the risk of electrical noise and interference. This may involve using isolated ground receptacles, shielded cables, and other specialized grounding measures. Always remember that working with electrical systems can be dangerous, and it's important to take all necessary precautions to protect yourself from electric shock. This includes wearing appropriate personal protective equipment, such as gloves and eye protection, and following safe work practices. When in doubt, always consult with a qualified electrician or electrical engineer. They can provide expert guidance and ensure that the electrical system meets all applicable safety standards. Hopefully these examples have helped to underscore the importance of proper grounding techniques and the potential consequences of making mistakes.